Well, here we go, ladies and gentlemen. Chapter 11. Trig was fun, but we're moving on. Uh, that has gone through its cycle. Okay, all right. So as you can see, we have this kind of sketched out for the next, week and a half. Um, we can, I can post all this so you know the schedule, but probability is so amazing once you get your head wrapped around it, how powerful it is and how many decisions are made. So this is a good one. Here we go. So this is a kind of a table of life expectancy from Australia. So people take data, they take data, they take data, and then they kind of create things that they can use to make predictions. So, I just wanted to, it's a lot of numbers, but if you're looking here, we've got the male at 20 years old. Out of 100,000 people, 98,052 were left, and with a life expectancy of 54 more years. So great. Should shoot for about 74 and 3/4. But it's not linear. So I wanted to illustrate that by, if you have a 60-year-old, yeah, a few less, make it that far, but look at their life expectancy. Now they're looking to make 78. So it's kind of like this is what people base the life premiums of life insurance. It's like, well, if you're young, then we'll have you pay this much because we think this is going to happen. But if you're older, well, yeah. So, some things to kind of ask yourself about this is, can you answer some of these questions? Can you use the life table to estimate how many years you can expect to live? Yeah, I think we can do that. We have it. Do we believe it? Um, and so forth. So basically, data creates our predictions. All right. So hold on to that thought. Um, Probability 0 to 1. If you have a 150% chance of something happens, then you need to walk away because that's just weird. You have probability is a number between 0 and 1. But then we transfer that by putting it in percentage, and we usually say something 0 to 100%. Impossible to certain. It's kind of like, what's your risk factor? What's your probability? How safe do you feel? Stuff like that comes up a lot in your life. All right, so we're going to obviously in this class is find probabilities, and the way you find probabilities is you have some formulas, but we're going to drive all those formulas so you kind of know where they come from. Uh, uh, but I want you to know there are really two ways to find probability. One, if you want to find the probability of, I don't know, throwing the water bottle up in the air and seeing how many times it lands on the cap, you can do it 1 billion times. And then you can count how many times it worked and how many times it didn't. And basically, you can say that's the probability. So when you do something a large amount of times, you can trust the results to be like, hey, this is kind of what predicts it. So that's called experimental probability. And believe it or not, that's what we use most of the time because it's hard to calculate theoretical probability, and that's using mathematical formulas, maybe area over an area, stuff like that. Um, so the whole calculate part, that's certainly what we'll do. There's these things called Monte Carlo simulations, and that's kind of more that you're using um, a computer just to repeat the process millions and millions and millions and millions of times to create these. So it's pretty cool. You'll see those later in your life, I'm sure. All right. So experimental probability, some of the vocabulary that you're gonna need is how many times you're gonna try something. What are the outcomes? So, if you roll a die, 1, 2, 3, 4, 5, 6. Beautiful. Frequency is kind of the number a certain outcome happened, and relative frequency is the frequency expressed as a fraction over the total number of times you did something. All right. So if we rolled a die and we rolled it 100 times and 20 of those times we got a 5, we'd say the frequency of rolling a 5 is 20. The relative frequency is 20 over 100. All right. Experimental probability is equal to relative frequency. So in other words, we will say the probability of rolling a 5 is 20 over 100. Of course, we'd reduce that to 1/5. And you're kind of going, no, that's 1/6, Mr. Sayers. Well, maybe it was a weird die. So you got to consider that. So here's another situation where we have these weird cones, and you could throw cones down. Great. So we did it. It was super fun. I'm sorry you missed it. And we did it 279 times. Fantastic. Miss Lewis is getting really good at it. And it turns out it landed on its side 183 times and its base 96 times. All right. So we'd say the number of trials, 279. When we list the outcomes, in this case, we just list side and base. And the frequencies, we list the numbers that had happened, and then the relative frequency of the side and the relative frequency of the base. So we would say that we expect it to land on the side 60, we have a 65.6% chance of it happening, or we'd say we expect it to happen 65.6 times out of 100. So different ways to say the same thing. Ooh, this was really exciting. I was getting pretty good at it. So we took these sharp tacks and threw them at people. I mean, threw them down on the ground. And what did we get? Well, two things could happen. They could both land on their backs. Okay. They could back and a side and two sides. Hey, ask your folks about a game, pigs in space. No, there's some game that had two pigs, plastic pigs, and you roll them and how they'd land aside, and they had all these hilarious names for it. So it's pretty fun. But I digress. So I got 5 of my closest friends, and we all threw the tacks. 2 times or 20 times. So we got our data here. And what you'll find is in these tables, you definitely really want to deal with the totals. So, the outcomes are 2 backs, back and a side, 2 sides. The frequencies 30, 50, 20, and the relative frequency then is 30 over a total of 100, and so forth. So we would basically say there's a 30% chance we'd get 2 backs. All right. So tonight's homework is all about, can you pull the information off of the data? All right, so I think maybe I'll fly over here. All right, get out of the way a little bit. So here's, it pushes your ability to look at graphs and kind of read the right information. I'll just illustrate this one right here and just kind of say that in English. 11 days, I received 2 phone calls. So I received 2 phone calls on 11 separate days. That's probably a little bit better. Okay, so that's kind of how that is. Part A, how many days did the survey last? So, you're looking at these numbers. Is it 12? Is it 8? But you got to remember, every single bar represents that many days. So, part A is the sum of the frequencies of each outcome. Okay, so I had 2 on 0 calls. I had 9. 7. Sorry, I was like, what? What happened? I had 7 1 call days. I had 11 2 call days, and so forth. So I added up all the frequency, and I had a total of 43 days. So this is going to help us give us that relative frequency. All right, so estimate the probability of no phone calls. Well, no phone calls is, now I figure out the frequency of no phone calls over the total. Days with no phone calls, 0.4. All right. Whoa, whoa. Dink. Okay. All right, let's just roll this up. 5 or more phone calls. So now I'm looking at how many I had on 5, on 6, and on, well, 5 calls, 6 calls, 7 calls, 8 calls. I add those up, 4, 3, 1. I get a total of 8 days where that happened, over 43.186. And finally, my good friend. Now this is important. This says less than 3 phone calls, less than 3 phone calls. So I'm really counting 0, 1, and 2. I'm not including the number of days with exactly 3. So reading those, very important. All right, data. So everything we do today is going to be like pull the data, and data can come in many ways and shapes. I did the frequency graph there. So two-way table is when you're combining 2 variables. So here, male or female versus their mode of transportation. So transportation and male or female. So that's pretty cool. You look at this and you kind of pull some information off, like 13 female teachers catch the bus to school. That's pretty sad. All right. So, or that's really good. I don't know where this is. I shouldn't say that. It's like, you just want all the teachers to drive Lamborghinis, right? Okay, so first thing you do is, in this problem, we have a theme car. These people are coming off the ride, and if you're like me, I am just about to throw up on you if it's a little whirly ride. I am just not good at those, so I may dislike the ride if that happens. But we have child, adult, like or dislike. So we have this data. We have this data here. Now the data doesn't mean much. What we really need is the totals. So this may be the first thing you do with a table is make sure you've added them up horizontally and vertically. Okay, so it really helps us grab the right information. So part A says liked the ride. So I go to like. I don't care if it's a child or an adult. It turns out there's 83 people that liked it out of the total of 130. So it makes it easy. 83 out of 130, 0.64. Beautiful. Hey, what about is a child and dislike the ride? So how many people satisfy that? Well, right here, the child, sorry, the child and dislike the ride. So there are 17 that satisfy that out of the total 130. Once again, pretty easy. All right, so is an adult or dislike the ride? So here is where things can go south. People grab the number of adults and grab the number of dislike, and then they add it, and that's not right. It just seems like, what? So just think, this 47, where'd it come from? It came from 17 plus 30 equals 47. Where'd the 58 come from? Well, that's 28 plus 30 equals 58. Do you see how we counted this 30 twice? So we actually need to subtract it off once. I know. You got to be careful. You got to be careful. So that's one of those, and I'll bring your attention. It'll come up later in this chapter. The word "or" kind of is helping you decide that you need to watch that. So please be a little careful, and you're going to be fine. The final section today is sample space and events. So this is where we're starting to organize the information. The sample space is usually a set, and that set U is also called the universal set. So the universal set is the set of all possible things. Sure, we can say that, and it's like, wow, that's a big set. Well, we kind of like the universal set is all the outcomes of rolling a die. So that set got a lot smaller, didn't it? Because the only things in there are 1, 2, 3, 4, 5, and 6. All right, an event is something that is like special about some of those outcomes. It kind of groups those outcomes. A particular property. All right. So some things that come from a set notation is the sample space, all the outcomes, is called the universal set U. Good. The outcomes are the elements, so those are the things in the sample space, 1, 2, 3, 4, 5, 6. 1 is an element of that set. And events are subsets, groups of elements in the sample space. So you have to say it out loud right now. You should be saying it out loud. Sample space, elements, subsets. So it's good for you. All right, so we're going to list these things in set notation. Let's go ahead and do a quick example. Before we do that, of course, we got to talk about complementary events. Those are not events that say, "Hey, you look good. Oh, you're nice job on that dinner last night." It's not that kind of complementary because it has an E there. Those are with an I. All right, complementary events are just like two events or that make up the whole thing. So when you roll a die, you can get an odd. Hey, I'm going to say the event is an odd outcome, but you could also say then the complementary is an even number. There's no overlap of the two subsets, but the two subsets cover the entire set of possibilities. It really needs to be two sets to be complementary sets. You don't really say there's three, okay? Sure, you can have three, but then we go on and use different vocabulary for that. We'll get there. So look at that. They're going with the normal dice rolled. Let the event that it's a prime number. Oh, that's cool. So you either get a prime number or you don't get a prime number. So let's go through this. Use the set notation to list the outcomes in the sample space. Well, I've done the first one for you. This is where you're using that cool little squiggly brackets. 1, 2, 3, 4, 5, 6. That's all the possible outcomes. Now, A is the event that is a prime number. So, are you sweating it? Because of course I would call on you to write down of those 6 numbers, which ones are prime. 1 is not a prime number. Oh man, it kind of actually used to be in the early 1900s. It was kicked out, believe it or not. The definition is it's divided by 1 and itself, implying itself is different than 1. So there you go. So 2, 3, 4 is not because 2 goes into it. 5 works, and 6, darn. Okay. So A prime is the notation for a complementary set. That's everything else. You don't have to think, oh, which ones are not prime. No, you just list everything that you didn't list earlier. So that's 1, 4, and 6. Awesome, well done. All right, so when we draw a Venn diagram is just kind of a good way to like organize the data in a picture. A rectangle is always used for the universal set. So everything in that rectangle are the outcomes. So I could just put a 1, 2, 3, 4, 5, 6 randomly. Perfect. That's the universal set. What we do is we could put a circle or some kind of shape in there and say anything inside that satisfies the properties, the particular property of set A and so forth. So we know that 2, 3, and 5 satisfy A. We need to find 1, 4, and 6 can be floating around anywhere. And so that gives us the universal set. It says what elements satisfy A and what don't. All right, that, believe it or not, is all there is about the universal set. All right, two-dimensional grids and trees. These are so basic and easy that I'm not going to really do very much of that. So we're doing two things simultaneously or one after the other. We kind of gives us a way to look at all the possible outcomes. If we flip 2 coins, we get this is coin 1, this is coin 2. Oh, okay, I have it written right there. We can get a heads tails on either. So this dot right here means we got a heads on both. This dot right here, we got a tail and a head. So it's just kind of a good way to say, hey, there's 4 possible outcomes because I can count those. Here, we get a heads on the first coin, and we can still get a heads or tails on the second coin. The list here is kind of saying, hey, we got heads, heads, let's write that. Heads, tails, let's write that. So you can do this list if you want, but this is really the tree diagram. Pretty cool. Just did a few quick examples. You can check them out on the notes if you want. I roll a die, flip a coin. Looks like there are going to be 12 possible outcomes when I flip a coin and roll a die. I can get a 3 and a tail. Beautiful. A spinner. We all have those a lot, I guess. Spinners come up and they're very popular in this chapter. I've never really seen one except for playing Twister. So ABC, you got 3 outcomes, you got 6. There are 18 possible ways in which that could happen. Pretty cool. I'm not a big fan of grids. I think they're boring and it's just like, oh great, bunch of dots. Now tree diagrams, I definitely have a crush on those. They answer so many questions in this chapter. They kind of just hold it and present it in a way that you can pull, like leaves or fruit from it. Oh, that works good. So really, tree diagrams, we're definitely going to want to do that. All right, tossing a 5 cent and a 10 cent. I don't understand that. Why are they 5, 10, quarter? It just means they're heads or tails. So that's what they're saying. Coin 1, coin 2, and we just saw that. Spinner. Which one goes first? Why don't we do the ABC and then heads, tails from that? You can. So order is not defined. You can put those in any order. You could do the ABC and off the ABC put a HT, HT, HT. Same thing. That's it. Darn it. Trying to get it under 20, but I did a lot better than live because I sure would have had fun. All right. Good. Hope the quiz is going well. That's going to be due on Wednesday. So please bring that in. Maybe clean it up as much as you can. But see you later.